Okay, welcome back to our forces unit. Today we're going to be talking about two forces that we've been drawing so far, but we haven't really mentioned them by name. Or I guess one of them we have, one of them we haven't. We're going to be talking about weight and also a force called the normal force. The definition of weight is the force exerted on an object due to gravitational effects. And you see that word gravitational in there and you think gravity. That's the most important thing here, okay? Weight is exactly the same as the force of gravity. They are synonyms. They mean the exact same thing. It's not that weight has some relationship where if you have the weight, you can calculate the force of gravity. If you know the weight, it is the same thing as the force of gravity. It's just two different names to refer to the same thing, weight and force of gravity. Objects that are floating in space, like satellites up in the sky, the moon, etc., we can say that those objects have weight, but usually if it's not something that's very close to Earth's surface, we refer to the gravitational force on them as just the force of gravity. If it's so we could talk about the force of gravity between the moon and the Earth. We don't really talk about the weight of the moon because it's not something that's on Earth's surface. If it's something that's on or near Earth's surface, we want to talk about the gravitational force between the object and the Earth, we usually say it's weight. Okay, that's what we call it. One thing that I need you to remember is that weight is not the same thing as mass. Do not forget this, and we'll see in a second how they're related, but they are not the same thing. Weight is a force, therefore it is a vector, and it has a direction. Okay? Don't get this wrong. This was actually a question on the Regents at one time. It asked what, it was one of those questions where it gave you four options and said which of these is a vector, and one of them was weight. And a lot of people did not remember that weight is a force. It points straight down. It is not just a number. The direction of weight is always straight down. All right. So you should have done a lab, hopefully at this point, that is the weight lab, where we measured objects' masses and we measured their weights and we plotted the weight versus the mass. And the graph ends up looking like this. It's a very simple graph. It is a straight line. Another way of saying that is that this graph is linear or directly proportional. And it has a y-intercept of 0, technically 0 newtons. And when you did this lab, you should have noticed that sometimes when we get a line of best fit, the data points are really scattered around it. This shouldn't have happened here. It should have been a very, very tight fit. Was there a lot of scatter to the data points? No. That implies that there's a very strong relationship or correlation. So that means that that's good evidence that there is a distinct and definite relationship between weight and mass. If it had been very scattered data points, you might say, well, it's suggestive of a pattern, but maybe it's not all that accurate. This seems to be very accurate. We're going to determine the relationship between weight and mass right now. We're going to analyze the equation of the best fit line. We know this is linear, and we know that for a straight line, we have this equation, y equals mx plus b. We're going to start off by changing the variables to reflect what's on the axes. On the y-axis is weight, and the symbol for weight, we said it's the same as the force of gravity. They mean the same thing. And on our reference tables, we see that the symbol for the force of gravity is Fg. So I'm going to change this to Fg equals, that m stands for the slope, and I'm going to just write out slope here. The reason I'm going to do that is because what's on the x-axis? That would be mass. So I'm going to change this to Fg equals the slope times the mass plus b. And what should the y-intercept be? We already said that it was 0, so our equation has changed to this. Fg equals the slope times the mass. Okay? So maybe the slope stands for something. Maybe it's something important. One way that we could see if that's the case is, let's take a look at the units. I know that the slope can be calculated by doing the change in y over the change in x. The units on the y-axis are newtons. Remember, brackets means that we're just looking at the units here. The units on the x-axis are kilograms. Now, Newton per kilogram, that is actually a legitimate unit, but it doesn't really mean anything to you right now. Do you remember back when we talked about what a Newton was really equal to? We said that it was equal to a kilogram times a meter over a second squared. So on top, I could rewrite Newton as kilogram times meter over second squared, and on the bottom, I still have kilograms. What do you think is going to happen now that we have a kilogram on the top and a kilogram on the bottom? They should cancel out. That'll leave me with units of just meters per second squared. And I apologize that this writing is so small, but that leaves me with units of meters per second squared. Those are the units of acceleration. And you should remember from the lab, we got units, we got a value for the slope of about 10. Everyone was about 10. And then if the units are meters per second squared, then the slope is 10 meters per second squared. Now that's really, really close to an acceleration that you've used multiple times so far. Okay, an acceleration that's measured in meters per second squared and is very close to 10. Think about it. Isn't that really close to 9.81 meters per second squared, which is known as the acceleration due to gravity, and is represented by little g? When we did the weight lab, the slope of our graph was the acceleration due to gravity. That tells us what the relationship is between the force of gravity and mass, or weight and mass. If you know the mass, you multiply it by the acceleration due to gravity, and you have the weight. If you have the weight, you divide by the acceleration due to gravity, and you have the mass. So anytime you have one of those numbers, if you also know the acceleration due to gravity in that location, you automatically know the other one. Okay? They are not the same thing. We are not saying Fg is equal to m. We are saying Fg, the force of gravity, the weight, is equal to mg. This equation, in a slightly rewritten form, we can rewrite this as g equals Fg over m, is on the reference tables right here. We skipped these equations for right now. We're going down to this equation right here. G equals Fg over m. Okay? Ref tables. This is a really simple equation, but it's very important to understand forces. The force of gravity is almost always an important force to consider. Also, do not confuse this with the other force equation we have learned so far, F net equals ma. They look the same. Okay, the equations look very similar, but they are totally different. F net is not the same thing as Fg. Fg is the force of gravity, or the weight. F net is the sum of all of the forces acting on an object. Not the same thing. A is an acceleration. G is the acceleration due to gravity. We have to be specific when we're talking about G. It is the acceleration due to gravity. Okay? So those equations are not the same thing. Do not write one when you're really trying to use the other. The symbol in the reference tables for weight is Fg, but you can also see it listed sometimes as W. Okay? Just as a capital W, which I guess can get a little confusing when we get into another unit, but you should understand weight and force of gravity enough by then to know the difference. Let's do some quick examples. On Earth, what is the weight of a 10 kilogram object? This is extremely easy. Fg equals mg. The force of gravity, or the weight, is equal to the mass times the acceleration due to gravity. Fg equals 10 kilograms multiplied by the acceleration due to gravity. Even if you forget what that is, it's on the reference tables for you. Acceleration due to gravity on Earth is 9.81 meters per second squared. 9.81 meters per second squared. I take 10, I multiply by 9.81, and I get 98.1, and the units of weight would be newtons. Okay, another difference between weight and mass. Weight is measured in newtons, mass is measured in kilograms. On Earth, what is the mass of an object that has a weight of 19.62 newtons? So now we're going the other way. This time, we have the weight, we're looking for the mass. The weight is 19.62 newtons. Mass is what we're looking for. and g is 9.81 meters per second squared. You're going to get really used to seeing g as a constant here. So we take 19.62, divide by 9.81, and we get 2 kilograms. By the way, a useful thing to be able to do, since the acceleration due to gravity is almost 10, you can estimate very easily what the weight or mass of something is. If you know the mass and you're trying to estimate the weight, multiply by 10, as long as we're dealing with Earth. If you know the weight and you're trying to estimate the mass, divide by 10. Okay, let's move off of Earth for a bit. On the moon, an object with a mass of 5 kilograms has a weight of 8 newtons. What is the acceleration due to gravity on the moon? Even if we're not dealing with Earth, we can still use this equation to solve for g. And I do want to point out, by the way, that g is called acceleration due to gravity or gravitational field strength. Okay, those mean the same thing. So if you ever see a question asking about gravitational field strength, you're just solving for little g. Also, if you ever see units of newtons per kilogram, like we did on the front, those are equivalent to meters per second squared. We could have been doing in this entire time our units for acceleration in newtons per kilogram. That's one option. We can do that. But we usually just use meters per second squared. Okay, just wanted to point that out. Anyways, back to our problem. The weight of the object on the moon is 8 newtons. The mass is 5 kilograms. We're looking for g. 8 divided by 5. Oops. 8 divided by 5 is 1.6. 1.6 meters per second squared. Okay. Now, last example, pay very close attention to this one. An object with a mass of 7 kilograms on Earth is brought to another planet where the acceleration due to gravity is only 6 meters per second squared. What is the mass of the object on this other planet? Now, if you're not paying very close attention, what you're going to do is you would take 7 and multiply by 6 for the acceleration due to gravity, and you get 42 newtons. And that would be the weight on the other planet. But that is not what was asked for. This question asks for the mass. Remember the definition of mass. Mass is the amount of matter. It's the amount of stuff contained in an object. Is the amount of stuff that is contained in an object going to change if we go from one planet to the next? No, the number of atoms is still exactly the same. The number of particles is still exactly the same. The mass does not change. Okay? The definition of mass means that it shouldn't change if you bring it from one location to the next. It's not location dependent. However, the weight of the object is, because on different planets there are different accelerations due to gravity which cause differing gravitational effects. So the key here is that the weight does change if we bring an object to a different planet. The mass does not. So read very, very carefully whether we're talking about mass or weight in different problems, and that'll help you to determine what you should do for your answer. Okay? So in this case, since we're asked about the mass, it's very easy. We know the mass does not change if you bring it to a different planet. The weight does, the mass does not. I want to spend the last bit of this video talking about the normal force. It's a force that you've been drawing, we just haven't referred to it as the normal force. Draw a free body diagram for a book that is at rest on a table. Also include the equations for net force in both the x and y directions. So I'm going to draw a real quick free body diagram. Book. Here's my axis. We'll just go with the standard x, y, positive. I know that one of the forces on the book, on the table, must be a downward force of gravity. I'm going to label that Fg. And normally I would draw an upward force from the table and I'd label it F table or something like that, or F surface. But now we're going to learn the actual name for that. That force is called the normal force. The force from the table on the book is the force that keeps the book from accelerating downward due to gravity. It keeps it from being in free fall. That force is very specifically called the normal force. And it's symbolized as Fn. Not F net, Fn. You're going to have to know the difference between Fn, the normal force, and F net, the net force. The net force is the sum of all the forces acting on an object. The normal force is the force that acts when an object is in contact with something, like a table or a surface or the ground. We call it the normal force because in physics and in math, normal means perpendicular. It's a synonym for perpendicular. Okay? When you were in geometry, you probably talked about normal lines at some point, or you might have. That is what we're dealing with here. We're dealing with a force that is perpendicular to something. The normal force always acts perpendicular to the surface, an object either rests on or is in contact with. That's what the normal force is. Normal force results from being in contact with some surface, and the normal force is always directed perpendicular to that surface. So in this case, the book is on a table. We can assume the table is horizontal, so the normal force points vertically. Don't get into the trap of always thinking the normal force points vertically. 95% of the time, that's correct. But what if you have something that is held against a wall? The normal force would not be vertical in that case. It would be perpendicular to the wall, so pushing outward from the wall. If you have something on a ramp, the normal force is not straight upward. It is perpendicular to the ramp surface, so it is inclined at some angle. So let me give you those examples. So here's something on a wall. Wall, object, Fn. Notice here's the wall, here's the normal force, it's perpendicular. Here's an object on a ramp. Ramp, object, normal force. Okay, so just keep that in the back of your mind. We won't deal with those situations for a little bit yet, but it's important to know. Let's do one example quick. A man is pushing a box horizontally across a frictionless surface. Let's draw a free body diagram. Oh, we never wrote net force equations for this. Let's do that real quick. There are no forces in the x direction, so we have F net x equals 0 newtons. And in the y direction, we have Fn in the positive y direction minus Fg, because it's in the negative y direction, equals MAY. Okay, those are my net forces. I can actually also say that that since this book is on a table, it very clearly is not accelerating up or accelerating down. It's just at rest on a table, and it's remaining at rest. Therefore, the acceleration is 0, and if I add Fg over to the other side, I can say that the normal force is equal to the force of gravity. That's an important result, and we're going to see why that's an important result as we do this second example. Let's draw a free body diagram for the box. Man's pushing it horizontally across the surface. So I have box, frictionless surface I should say, axis. We have the force of gravity pointing down in the negative y direction. We have, I'm going to start calling this, if you have a person or an animal or some sort of being pushing a box or pushing some object, we are going to start calling that the applied force, F applied, or just FA if you want. And upward from the ground, we have the force from the ground, which we are now calling the normal force, Fn. Let's write the net force equations in the x and y directions. In the x direction, there is simply an applied force, so I write F net x equals F applied equals MAX. And in the y direction, F net y, there is Fn in the positive y direction, Fg in the negative y direction, so it gets a minus sign in front of it, equals MAY. If the mass of the box is 50 kilograms, what is the weight of the box? Simple. We know that the equation for weight is Fg equals mg. If the mass is 50 and acceleration due to gravity is 9.81 meters per second squared, don't forget those units, and don't write them as meters per second, we know the weight must be 50 times 9.81, 490.5 newtons. What is the normal force on the box? Well, for this is not an easy one-step calculation, okay? There's no equation for the normal force. When I say that, I mean there's no equation on the reference tables for the normal force. We need to use our net force equations that we created after we drew our free body diagram to solve for the normal force. We know in this case the man is pushing a box horizontally. Again, it does not say anything about the box getting accelerated in the vertical direction. It's not accelerating upwards. It's not accelerating downwards. It is simply moving horizontally. If it's not accelerating in either of those directions, then the acceleration in the y direction must be 0. And that means that if the difference between these two forces is 0, guess what? They must be equal to each other. And if they're equal to each other, and we already know what Fg is, 490.5 newtons, well, guess what? That means the normal force must also be 490.5 newtons. Okay? So, the conclusion here is that an object that is not accelerating in the y direction on a flat surface with only Fn and Fg as vertical forces leads to the conclusion, in that situation, Fn equals Fg. Now, it might sound like those are a lot of steps to get to that conclusion. That's a very common situation. For an object that's on the ground that is not accelerating in the vertical direction, okay, it's not changing its speed up or changing its speed down, it's just remaining at rest in the vertical, in the vertical direction. And the only forces in the vertical direction are Fn and Fg. They must be equal to each other. That's something that we're going to see a lot. Now, if the applied force is 20 newtons, what is the acceleration of the box and in what direction? We already said that there is no acceleration in the y direction, so if there's acceleration, it must just be in the x direction. We already have our net force equation, so I'm just going to take that. F applied equals max. The applied force is 20 newtons. The mass of the box is 50 kilograms. And we can solve for the acceleration. Ax must be equal to 20 divided by 50, which is 0.4 meters per second squared. Okay, we're getting lots and lots of practice with solving net force equations based on what we're given. That's pretty much it for this. We've talked about the weight and the normal force. If you have any questions, let me know. I'll see you next time.